Before we're going to do a review first. Chapter 1, 2, and 3, using the review document that I handed out. Everybody's got a copy of that, I assume. Okay. So what I'm going to do first is share my copy. Get it up on the board. Sometime this year, I hope. There it is. Let's fill the screen. You'll see that from the back over here, maybe. Does that need to be twisted more so you can see it? No, that's good. Okay. Let's see. Maybe I can change the increase that a little bit. All right. So I believe this document is sequential from, yeah. Okay. So I don't have to put the chapter up here. It'll just walk its way through sequentially from 1 to whatever. And that way you can identify which one we're on. So I picked out some of them that I think are relevant and are not repeated. There's a lot of repetition in these review documents that I create just to give you lots of practice. It's kind of like those psychology tests they give you. Have you ever taken one of those? Personality tests and psychology tests. A lot of the questions are exactly alike, only they word them differently to test to see if you're given a valid answer, I think. So that's kind of along those lines. So I've just picked out the ones that are not repeated, hopefully. Sometimes I mess up and there's a repeated one. So let's start off with, first of all, when you went through this document, were there any in there that were particularly troublesome? Well, I want to get those out of the way first, before I start talking. Or if you think of one while we're in the middle, right, let me know. We'll get to that one immediately. I don't want to leave anybody hanging with one of these problems that they don't understand. Otherwise, I'll just go through the ones I've marked and maybe that'll click something. Okay. Start with number 2. All right. In which of the following pairs of properties are both properties chemical properties? So we've got A through D with pairs of properties, and they both have to be chemical. So how about freezes at 10 degrees and is non-flammable? Well, that's a pair of physical and chemical. Right. The second one is chemical, the first one's physical. Decomposes at 500 degrees and reacts with bromine. Those are both chemical properties, aren't they? Yeah. So, test-taking technique. When you've got a multiple choice selection and you don't have any wonky ones in there, like none of the above, 2 of the above, all of the above, none of the above. I said that already, didn't I? Then once you find the right answer, you can go on. And we found the right answer at B. Right? Those are both chemical properties. Now, what's the difference between a chemical property and a chemical change? Or a physical property and physical change? Property versus change. Property references a potential for something. And it's static. But a change is just what it says. It has to describe a change, either a physical change or a chemical change. All right, let's see. What's the next one? So we skip a bunch of them. And 13. Which of the following statements about atoms is incorrect? This is a good example of details, right? You might if you like to speed read novels, does any of you just go through a novel in a day? No, nobody reads that fast. Well, I don't read quite that fast, but I know people who do. I mean, it's like, you ever seen that old movie? What was the one with the robot that became intelligent? Short Circuit. You ever seen that movie? When he's reading through a book, it's just pages are flying by. Some people can read almost that fast. Well, the problem with that is you miss the details. And here we've got a detail. Which one of the following statements about atoms is incorrect? Right? Not correct, incorrect. So that could throw you off if you're not careful. An atom is the smallest piece of an element that can exist and still have the properties of the element. Is A true? Yeah. Right. A is true. How about B? Free isolated atoms are rarely encountered in nature. As far as we know, free isolated atoms. Now you might find some isolated atoms in places in outer space, right, where the conditions are very extreme, but we're not likely to encounter any in this environment. They seem to, nearly all of them occur in compounds. And they're not single atoms either. You could have like gold. Pure gold is not easy to find, but it's generally not combined with other elements like most of the elements are. But isolated atoms are rarely encountered. That's true. How about C? Atoms may be decomposed using chemical change. No. No, you got to get more aggressive with atoms to decompose an atom. We're talking about nuclear chemistry, I guess, nuclear chemistry. Right, so there's your false one right there. And again, we don't have any wonky ones. Right. D says only one kind of atom may be present in a homoatomic molecule. Is that true? Yeah. Homo means same atom. So the molecule can be composed of a bunch of different atoms, but they all have to be the same element. What are some examples? How about the diatomic elements? Right, those are homoatomic. Right. Right, so forth. Or I don't know if we've encountered this one in this class, but most commonly, solid sulfur is a combination of 8 atoms. All right. That was 13. (21) and 22. Which of the following is a property of both liquid state and solid state? All right, so if you've got a liquid and a solid, they both have definite volumes, correct? Both have definite volumes. The difference is this one has a definite shape and this one doesn't. Okay, so definite shape, nope, that's not it. Indefinite volume, they both have definite volumes because that can't be right. Indefinite shape and definite volume. Now it's just flip, right? Well, actually, indefinite shape would be true for this one, but not for that one. Definite volume, yeah. Is that it? Let's see. An indefinite shape is good for the liquid. Right. Okay. Definite volume. Okay, that's right. So C's not it. More than one correct, no correct. Right. None of them are right. Sometimes it's hard to talk and think at the same time. 22. In which of the following pairs of properties are both properties physical? Okay, we're still talking about properties, not changes. Melts at 73 degrees and decomposes upon heating. Decomposition is a chemical process, right? So it can't be A. Good reflector of light and blue in color. Yeah, that's true. It reflects light, can reflect light, and its color is blue. Those are physical properties. Yeah. So B is correct. Right. How about C? Has high density and is very hard. Yeah, those are both physical properties. Right, so we got two of them that are right. That means more than one is correct. So D is the correct answer for that. I try not to look at the answers until I'm finished. $30. Which of the following statements concerning elemental abundances in Earth's crust is correct? Abundances of elements in the Earth's crust. Okay. One element accounts for over half of all atoms present. Yeah, that's true. Right. So we're talking about over half of all the atoms present. So we're talking about atom percent, right? Not mass, but atom percent. Which one would that be? I'm sorry? Oxygen, yeah. Why is that? You remember? Goes back to a couple of questions ago, right? You don't find any, mostly elements, you don't find them not combined with something else. Most of the metals in the Earth's crust are combined with oxygen. I just read an article this morning. The last rover that we sent to Mars had a little device on it that they were testing to see if they could make oxygen from whatever there is in Mars. And it didn't really say what the source was. Right? Sort of implied that you could get oxygen from the atmosphere. There's probably some oxygen there. Most of it's carbon dioxide, but maybe you get some oxygen there. But you could also, what color is the surface of Mars? Red, yeah. Why is it red? Right. If you'd ever lived in Georgia, you'd know red because the soils are red down there. They're red because of iron oxide in the soils. So that's more than likely what's causing the red on planet Mars. So all you have to do, all you need is a good source of energy to break apart those bonds between the iron and the oxygen, and you got oxygen gas. So what do we need oxygen for? Right. That's first and foremost breathing. It's also an oxidizer for your fuel. Right. If you want to get there and refuel your craft and get back, you're going to need two things. You're going to need actually they call oxygen fuel, but it's not. Fuel is most likely going to be methane because methane is fairly easy to come by. And oxygen is the oxidizer, right? You know, these rockets that Elon Musk and SpaceX are sending up, and there's a couple of other companies that are using the same technology. Their rockets are based upon methane, liquid methane, and liquid oxygen in those tanks that they carry and combine them in the rocket engines. Okay, I'm not going to waste any more time, many more of your time on that. So that one element, yes, is over half of the composition of the Earth's crust. 33. What's the biggest obstacle to Elon Musk putting another rocket into space? Actually, there are two obstacles, but they're in cahoots. Government and environmentalists. They're keeping his rockets grounded because that's what they do. Which of the following pairings of terms or concepts is correct? So let's see. A, an atom paired with a limit of physical subdivision. Well, let's see. Physical subdivision could bring you down to atom, or it could bring you down to a molecule, right, or the compound. Right? So maybe A is not the best answer. Because to break those bonds, if you want to get down to the atom, you have to break some bonds maybe, and that's chemical. So A is not a good choice. B, molecule, the limit of chemical subdivision. That's just the opposite of A. Right? Molecule is the limit of physical subdivision. How about C, a compound, a homoatomic molecule? No, it has to be heterotonic. You got to have at least two different elements to have a compound. Right? You can still have a molecule with the same elements, but you can't have a compound unless there are at least two different elements combined. All right, so more than one correct response. Well, that's not right. Which one is correct? There's something wrong with that answer, isn't there? Huh? Yeah, none correct. So that should be E. There we go. I'm sorry, does yours have it different?
Yeah, all the
Okay, that's good. I just didn't change my key. Okay. That's another reason I go through these. I find mistakes. Okay, I better save that. There we go. Okay, 34. All right. In which of the following pairs of chemical formulas do both members of the pair have the same number of atoms per molecule? Okay, so just count up the number of atoms. This is to check to see if you know what the subscripts are for. All right, so A has how many in the first one? 1, 2, 3, 4, right? Has 4 atoms in the first one. How about the second one? 1, 2, 3, 6. Right. Right, so that's not it. How about cobalt chloride? That has 3. C. This is a good illustration of if you write the symbol wrong, you got the wrong element, right? C little o is cobalt. C big O is carbon and oxygen. Okay, so if you're fond of writing everything in caps, you need to break that habit, at least for writing elements. Okay, I've had students that just can't seem to break the habit of writing in caps, all caps. So they write CO and it's wrong, right? If it's supposed to be C little o, and they write C capital O, then of course it's wrong. But this has 1, 2, 3, 4. 4 in the second one, right? So that's not it. How about O2N2? That's 4. And NH3. There we go. That's it. Only one correct answer. C. Now I just put the numbers up there. Everybody see how I got those numbers. Okay. That's 34. Let's move down to while we're passing through these guys, if you've had a chance to look, I hope you've looked at the review document. When you see these type with 3 statements and then A, B, C, D based upon those statements, like all 3 are true, 2 of the 3 are true, 1 is on, right? You have to look at all 3 of those statements to see which ones are true, right? And that really takes a lot of time because you got to look at each one. So If my memory serves me, if you see any of these, they're going to be bonus. Let me check to be sure. Yeah, I do have some bonus on this one. Actually, 47 points required and 10 point bonus. And yeah, there are several of them just like that in the bonus. All right, let's take a look at 46. If we have time, we'll come back to some of those others. For the elements calcium, iron, and beryllium, choose the appropriate characterization of the set's chemical symbols from the response list. Okay, calcium, iron, and beryllium. Calcium, right? What's iron? Fe. And beryllium? Be. Br is bromine. Nice try. Okay, so let's see. All symbols have one letter. Nope. All symbols have two letters. Yes. So B is correct. All symbols start with the same letter. No. All symbols start with a letter, not the first letter of the element's English name. No. Because calcium starts, beryllium starts with the first. Iron's the only one that doesn't match because it's based on the Latin. So B is the best answer for 46. 47, looks like we got a similar question here. Now we're based on silver, sodium, and potassium. How about silver? No. Not even a wild guess? Yep. AG for argentum. Sodium. Na for natrum. Both of those are Latin. And potassium. K. K for kalium. So all of them are based upon the Latin. All then not single symbol for all of them. All symbols have two letters. Yes. All symbols start with the same letter. No. All symbols start with a letter which is not the first letter of the element's English name. That D is the best answer. I'm sorry? Is D not the best answer? All symbols start with a letter which is not the first letter of the element's English name. So they're all based upon the Latin. Okay. All symbols have one letter? No, just one of them did. All symbols have two letters? No, just two of them did. All symbols start with the same letter? No. Yeah. Let's see, 48. Like we got several of these. Let's just, actually, these are to check to see if you know the symbols.
So we really make
You need to know the ones that I gave you on that chart with the red boxes around them. Right? You got to memorize those. Have you set up your flashcards? Some of you? I hope. Right, that's the best way to memorize them. Okay, 48. Let's see, we have iodine, fluorine, and nitrogen. Iodine, fluorine, nitrogen. Right, all single letters. So A is a good choice. They don't start with the same letter, but they do start with the first letter of their English name. So A, yeah, A is the best choice. They satisfy that one. 49, I think, is the next one. For the elements gold, lead, and bromine. Gold, AU, got it. All right. Lead, Pb. Plumbum, which means in Latin it means heavy. And bromine. Yep. Okay. They each have two letters. Symbols start with the letter, not the first letter of the element's English name. That one does, but these don't. All right, so D's not a good answer. B's the best answer there. And that brings up another point. When you have multiple choice tests, you only have those choices, right? So if you come up with an answer, say with a calculation, and your answer's not exactly in the list, if there's not one that says none of the above, then pick the best answer. If you're off by like the second or third digit, and there's none of them in there that match yours exactly, and you pick none of the above, but I say it's one of the others because I rounded off to fewer digits, then maybe you can make an argument, a case for points on that question. Now, if the question says round off to the proper number of significant figures, then you have no choice. Right? All right, 50. Silicon, sulfur, and tin. Silicon, right? Sulfur. How about tin? SN? Yeah. Stannum. They all start with the same letter. I was hoping we'd get to one of those. C, all start with the same letter. All right, how about 54? Give the classification of matter when two substances exist with the two phases present and the substance cannot be decomposed by chemical means. Classification of matter when two substances exist in two phases. That sounds to me like a mixture of some kind. Right? It's not a compound. It's a mixture, and you can separate the mixture by physical means. Cannot be decomposed by chemical means. Okay, what we have there, if you can't decompose either of the components by chemical means, they have to be elements. So we've got two elements in a mixture, and two different phases. Classification of matter when two substances exist in two phases and the substance cannot be decomposed. All right, cannot be decomposed by chemical means is it's an element, but we have a mixture, don't we? If you have two phases, oh, maybe it's an element in the gas phase or the solid phase and the liquid phase. How about that? That would work. Yeah. If you go to a jeweler's and they're melting gold to make some piece of jewelry, they throw gold into the crucible and they'll have some liquid gold and they'll have some solid gold that haven't melted yet. Two separate phases, but neither one can be decomposed. Okay, so yeah, pick the best answer. Element seems to be best. Anybody want to argue? Now's your chance. 58. A substance is composed of diatomic molecules. Choose the appropriate classification from the response list below. Diatomic molecules. Diatomic Now that there are diatomic elements, but you can also have diatomic molecules that are heteroatomic. You have two different elements together. Right? That's important to remember that. Could be an element or a compound. Yeah, could be either one. Right? It could be something like that. Or if we replace one of those nitrogens with an oxygen, could be that. They're both diatomic. Okay. But this one's homoatomic and that one's heteroatomic. So that looks like a good example. Yeah. I think A is the best answer for that one. All right. 66. Which of the following is both homoatomic and tetraatomic? So it's got to have the same elements combined, and there has to be four of them. Tetraatomic means four atoms, and homoatomic means they're all the same element. Yeah, that's the only one that makes sense. All right, 67. Which of the following substances is both heteroatomic and triatomic? Okay, this is heteroatomic. So it's got to have at least two different elements and three atoms combined. So HCN has three atoms and they're heteroatomic. Right? B is hetero, but it's only di. Actually, it's tetraatomic. C is tetraatomic, but it's homoatomic. Right? And D has 2, 3, 6. Right? So it doesn't fit. Right? The only one that works is A. Has three atoms, plus they're all different. Ooh, I left an answer out of that one. Maybe we ought to do that one so I can get that one filled in. Oops. So 69. Which of the following substances contains fewer atoms of one kind than the other kind? Okay. Fewer atoms of one kind than the other. All right. So HCN, you have equal amounts of each one, so it can't be that one. H2O2 has equal amounts of hydrogen and oxygen, so it can't be that one. P4 doesn't have to. So H2CO3, carbon is the least amount, hydrogen is the next, and oxygen's the most. So that D is the best answer for that one. Did I have that on the answer sheet? Okay. I don't know how I missed putting it there. All right. Now we're in chapter 2, measurements. 71. We're going to do some of that today, measure stuff. The mathematical meaning associated with the metric system prefixes: centi, milli, and micro. Centi, milli, and micro. What do they mean? All right. These are modifiers for a base unit. So they could be put in front of grams, meters, liters, whatever. And they will change the size of the unit that's being measured. But how do they change it? What does centi mean? No. Think of century. How many years in a century? 100, right? It's 100th. Centi is 100. Yeah. How about milli? -3. Yeah. 10 to the -3. And micro? Yeah, -6. It's a millionth of. Micro. Sometimes you'll see the Greek symbol. That's the Greek letter mu. And the prefix for this one against an element would be just the little c, little m, and the mu. Now, if you see a big M, what does that one mean? Mega. So it's 10 to the 6th. Right, so it's just the opposite of this one. How far apart are they? Have I talked about orders of magnitude yet? Orders of magnitude are the same as powers of 10. So if we are talking about 10 to the 3rd, that's 3 orders of magnitude. But usually we reference orders of magnitude in terms of differences. So the difference between this one and this one is 4 orders of magnitude. You increase it by 4. 4 orders of magnitude, powers of 10. So this one would be 6 plus 6 is 12 orders of magnitude difference between that one and this one. Micro?
Yeah.
No, you'd have to use this one. The mu. Have to use the mu. The capital M is mega. Okay. Let's see. Sometimes rather than write the micro, I'm thinking of medical abbreviations like microgram. I think they abbreviated MCG. Right, would be microgram in medical terms. They have, I think, medical profession has a phobia against Greek. They prefer Latin for everything. In fact, when I was in high school, some students that knew they were going into the medical profession were taking Latin, because at that time it was required in medical schools. You had to know Latin. But I think they dropped that down the road. And all the kids that were going to be chemists were learning German, because a lot of the original work at that time was coming from Germany. Right, about the time we got out of high school and got into college, Germany kind of went, and English took off. So everything published in scientific journals now is English, or if it's in another language, they at the very least they have a summary in English. Okay. Of course, what language do control towers and airline pilots talk all over the world? It's standard, required. English. Right? They always speak English when they're coming in, even if landing in Jakarta, right? It's all in English. Now in the cockpit, right, pilot and co-pilot, they may talk to each other in their native language, but when you're talking to the control tower, you talk in English. That was 71, 72. All right. In which of the following sequences are the metric system prefixes listed in order of decreasing size? So which ones do we have available? We have kilo, we have giga, we have mega, we have milli, we have nano, we have micro, we have pico, we have kilo. Oh, we already got kilo right there. And deci. I think that's all of them that came out of that list. Okay, let's put these in order of decreasing size. What's the biggest one up there? Giga. Giga would be that little g, and it has a value of 10 to the ninth. Giga. Gigabyte, billion bytes. Yeah. That's kind of gone by the wayside now, right? It's coming out in terabytes now, 10 to the 12th. In fact, this hard drive, this solid state hard drive I've got for my computer is 4 terabytes in that little package. The first hard drive I had in a computer for my work with the government was 78 megabytes. It's about that big and weighted. I mean, it makes a good boat anchor. Okay, so that's the biggest one. What's the next one? Mega. 10 to the 6th. All right. Next biggest one, kilo. 10 to the 3rd. All right. Let's see. Next biggest one. How about deci? 10 to the minus 1, 1/10. I think decimal points by tens. Next smallest one, milli. 10 to the minus 3. Micro. 10 to the minus 6th. Nano. 10 to the minus 9th. And pico. 10 to the minus 12th. Okay. So which one of those are in proper order? Kilo, giga. Giga's bigger than kilo, so that's not it. Nano, milli, nano. Micro is bigger than nano for B. So that's not the right order. Mega, kilo, micro. Mega, kilo, micro. That's the right order. Pico, kilo, deci, that's wrong. So C would be the best answer. Right. C. That tests to see if you know what these things mean. If you don't, that'd be a good one to study. '72, '73. Which of the following is an incorrect pairing of terminology? Okay. A, kilogram, metric unit of mass. Yeah, that's good. A is good. How about B? Milliliter, metric unit of volume. Yeah, I mean, it's not the fundamental unit, but it is a metric unit of volume. Yeah, that's true. How about C? Meter, metric unit of length. Yeah. So process of elimination, D is probably the wrong one. Okay. Cubic centimeter, metric unit of length. I think that was wrong. Cubic centimeter is what? It's a milliliter. It's a unit of volume, right? 1 cubic centimeter is equal to 1 milliliter. Exactly. Right. They're interchangeable. When do we use cubic centimeters and when do we use milliliters by convention? We use milliliters for liquids volumes, and we use cubic centimeters for solid volumes. What do we use for gases then? We got liquids and solids. What unit do we use for gases? No, we didn't cover that one. Usually cubic meters, especially when we're referencing density, because to get a mass, enough gas mass to weigh, you might take a cubic meter. Actually, that's not true. Let me see. Are we going to do that lab in here? No. Must be general chemistry. we determine the mass of a gas in a container on the way to determining the molar mass of the compound. All right, it's called the Dumas method. 76. In which of the following pairs of measured numbers does each member of the pair contain the same number of significant figures? All right, this is a brain teaser. How about 10.3 and 10.30? They have the same number of significant figures? Nope. First one has 3 and the second one has 4. Okay. Those zeros are significant for both numbers. The first one's significant because the 0 is captured between two non-zero numbers. The second number, 10.30, it has a captured 0 and it has a 0 to the right, and it's significant because there's a decimal. 800.0 and 80. 800.0 has 4 significant figures. How many does 80 have? Anybody want to take issue with that? Just 1. There's no decimal point in that number. I mean, there's no explicit decimal. So the 0 is not significant. 80 is 1. If you meant to have 2 and made a measurement and you're supposed to have 2, you need to put a decimal there. How about C? 0.0330 has 4 significant figures, right? The leading zeros don't count. How about 0.033? That has 3, 4 and 3. All right, so C's not right. Has different number. So process of elimination, D is probably the right one. 0.000096 has 2. 960000 has 2, because there's no explicit decimal there. All right, so D's the right answer. All right. In trouble with that one? No, okay. 79. The measurement 83109 expressed in scientific notation. 8310.9. So what does the coefficient have to be between 1 and 10? So we have to move the decimal 1, 2, 3 places over. And that gives us 8.3109 times 10 to the what? We move the decimal to the left. We were storing up tens, right? Tens, hundred thousands. Correct? And you can check yourself, right? Can we change this one to that one? Right? If we want 1,000 times that, 1,000 times 8 would be 8,000, right? Yeah, that's good. Just check yourself. Friend of mine at LSU, he was a neighbor in the apartment complex I was at, was a mechanical engineer student. And he says it amazed him at how many students for an exam, they'd studied one chapter. So they would be given a problem and they would try to shove a square peg in a round hole. They would take the data they got from the problem and shove it into the wrong solution. And it would give them a number. You're supposed to get a number in the range, say, just, I'm going to make something up, say in the range of 32.5. They come up with 3,500,000, and they don't see the problem because they don't have a way of estimating what the answer should be in the range, right? So I mean, that's what my calculator said, so that's what I put down, right? And you know, calculators, like any computer, what's the number one motto for computers? Garbage in, garbage out. You put garbage in your computer, it's going to spit out garbage. Right. So being able to estimate an answer is a good habit to get into, right? Does it make sense? 81. The calculator answer obtained from multiplying the measurements 64.49 and 6.57 is 423.70. Multiply those two. Okay, so we don't even need to know those numbers unless you want to check it to be sure, right? Maybe whoever wrote that problem is lying. 64.49 times 6.57 is 423.6993. Yeah, okay. Close enough. 423.70. What do they want us to do with it? Oh, they want us to round it off to the proper number of significant figures. Okay. How many are supposed to be in the answer? Anybody want to take issue with that? Now, 64.49 does have 4. How many is in 6.57? 3. So our answer, since this is a multiply divide rule, our answer can only have 3 significant figures. Right? So we count 1, 2, 3. That's a 7. So this one rounds up. Okay. 424 should be rounded the proper number. Now, what if we had, just for argument's sake, say we were supposed to add those two together. 64.49 and 6.57. Right? That's 6, 1, 9, 10, 10, 11, 71. Do we need to round that one? No, because there's the decimals, and there's the uncertain digit. That's good. We get to keep them all. So we have 4 significant figures in that answer. If we add them together, it's a different rule, right? Don't make the mistake of using the multiply divide rule for an add subtract. That was 81, 84. All right. According to dimensional analysis, which of the following is correct setup for the problem? How many milligrams are there in 85 kilograms? So we're starting with 85 kilograms, correct? And we're headed for milligrams. Right? So how do we set that up? We don't actually have to calculate it. The problem just wants us to go from kilograms to milligrams. Well, it looks like all the answers are chained. They have 2 conversion factors. One would go to, looks like the first one is going to grams. And the second one is going to milligrams from grams. See, so you get your kilograms canceled and your grams canceled. Well, now we need numbers in there. How many grams in a kilogram? 10 to the third, 1,000. Okay. How many milligrams in a gram? Same thing, 1,000 milligrams in a gram. Okay. So let's see if any one of those matches. Okay, 85 is right for all of them. Then we have grams over kilograms, right? So C's out, right? The first one is wrong there. 10 to the third kilograms per gram. That doesn't even make sense. It looks like B. Actually, we can eliminate all the others and stop here because B is the only one that gets it that far. We can check to be sure, right? 1 milli, okay. The conversion factor for B in the second position is not 10 to the third milligrams per gram, but 1 milligram is 10 to the minus 3 grams, which is true, right? M means milli. 10 to the minus third is equivalent to milli. So that's right. Did I lose anybody? No. Sometimes I wonder when I get blank stares back. Either you don't understand or you just get a bad hangover. 87. If object A weighs 6 grams and has a volume of 3 milliliters, and object B weighs 9 grams and has a volume of 2.25 milliliters. Now, technically, that's not right. If object A weighs 6 grams, has a mass of 6 grams. Right? So we tend to, when we're writing out word problems, we tend to use those terms interchangeably. So when we say weigh something, we're actually means determine its mass. B is less dense than A. A and B have equal densities. So we're looking at densities. So A density is what? A density is going to be 6 grams per 3 milliliters. 6 grams per 3 milliliters. What's that? That's 2 grams per milliliter, right? How about B? 9 grams divided by 2.25. 9 grams divided by 2.25. I don't know if I can do that one in my head. Four. Two significant figures, 2, 2, 2. All right, 4 grams per milliliter. So B is more dense than A. Actually, C, B is twice as dense as A. Yeah, that's true. Okay, so C is the best answer. '89. Which of the following comparisons of the size of a degree on the major temperature scales is correct? The size of the degree, that is, how big is that degree unit? Like if you move from 1 degree to the next, which one's bigger? Well, the best way to do that one is, first of all, recognize that the degree unit for Celsius and Kelvin are exactly the same size. So the comparison is between Fahrenheit and Celsius. Okay. So at what temperature does water boil? Celsius is 100 and freezes at 0. And Fahrenheit is 32, freezes, and 212 boil, right? So the distance here is the same. What's the difference here? Well, the difference here is 100. How about the difference here? Let's see, 0, 3 from 11 is 8, 180, right? So 180 units cover the same distance as 100 for this one. So which degree is bigger? Right? It takes fewer of these to get the same distance, right? So they have to be bigger. So the degree Celsius is bigger than the degree Fahrenheit. And there's that ratio, 180 to 10 to 100, right? Remember the formula? Well, I remember it this way. But that fraction is 1.8, ratio of 180 to 100. That's where that 1.8 comes from. All right, let's look at the answers. A Kelvin degree is larger than a Celsius degree. No, they're exactly the same. A Fahrenheit degree and a Celsius degree are equal in size. Well, that's not right either. A Fahrenheit degree is larger than a Kelvin degree. No, because a Kelvin degree is the same as Celsius and Fahrenheit degree is smaller. So a Celsius degree and a Kelvin degree are equal in size. That's the one. D. They're exactly equal in size. 92. How are we doing on time? Good. Yeah, I think we're still good. 92. In which of the following pairs of units is the first listed unit 1,000 times larger than the second one? Well, let's see. Let's see. A, B, C, D, and E. Is a milligram 1,000 times larger than a nanogram? Milli greater than nano. Well, a milli is 10 to the minus third, and a nano is what? 10 to the minus ninth, right? So that's 6 times. That's actually, this one is 10 to the 6 times bigger than the nano. 6 orders of magnitude. 1,000 is 3 orders of magnitude. So this one is 6. Right? That's not the answer. Liter and centiliter. Liter and centiliter. Right? So this one is 10 to the minus 2 of the liter. Right? The only difference there is 2. Right? That's not 3 times. It's only 100 times bigger. How about C? Kilometer and megameter. Kilometer and megameter. A kilometer is 1,000 times a meter, and megameter would be, right, 10 to the 6 times a meter. So that's only 3 orders of magnitude difference, right? Oh, that one would be right, wouldn't it? 1,000 times larger than the second one. Oh no, it's the wrong. Went the wrong direction. Sorry, it's a third, not a third. It's 10 to the minus 3. Okay. Anybody see my mistake? I was going backwards. I was dyslexic for a moment. More. I'm sorry. Yeah, right. And the way the question is worded, this one has to be bigger than that one in order to work. But this one is bigger than that one. So it's the wrong direction. And then D, more than one correct response. No, no correct response. D is the correct one. None of them are. Satisfy the conditions of the problem. 93. In which of the following sequences of measured numbers do all members of the sequence contain 3 significant figures? All right. A, B, C, D, and E. All right. How many is 3.03? Is 3 significant figures? 3.30, that's another 3. 0.033, that's only 2, right? Okay, so that's not it. B is 2 in that first one. 3 in the second one, 0.00780. That's 3 significant figures. And then 780 is 2. Right, so that's not it. 30.0 is 3. 0.300, that's 3. And 30100, that's 3. Right, those last 2 zeros don't count because we don't have an explicit decimal. So C is the right answer. Right. More than one, no. And the no correct response, that's not it either. So those don't count. '93. I looked at that a minute ago, didn't I? 95. Which of the following statements concerning the measured number 0.3030? 0.3030 is correct. We're looking for the correct one. D says more than one response, so there could possibly be two or more. So we have to look at each one. There are three, A, B, and C, we have to investigate in order to decide if D or E is possible. So A is only one of the zeros in the number is significant. Is A true? No, because that zero and that zero are both significant. Right? It's got two of the zeros are significant. Right? So A can't be it. Rounded off to two significant figures, the number becomes 0.30. Yeah, because this is a 3 less than 5, then we would round it off 0.30. So B is true. How about C? Expressed in scientific notation, the number 3.03 times 10 to the minus 2. Well, the original number, 1, 2, 3, excuse me. I don't need to move that far. Only need one. There we go. 3.030 times 10 to the minus 1 would be scientific notation. Okay. So C's wrong. All right, so only one of them is true. Right. B is the only true one. $95. Moving on. 97. Which of the following measured numbers contains three significant figures and has a magnitude of less than 1? Okay. Those are all in scientific notation. Right? So we need to find one that has that is less than 1. Right? How about A? No, A is greater than 1. A lot greater than 1. Right? So that was not right. B, is that less than 1? Yep. How many significant figures does it have? It has 3. 3 significant figures and less than 1. So that one's true. B is true. How about C? 3.20. That has 3 significant figures and it's less than 1 also, times 10 to the minus 4. Right, so that was true. So 2 of them are true. More than one correct answer. D. All right. 99. Which of the following measured numbers has an uncertainty of 0.01 associated with it? 0.01. So we're uncertain in the second decimal. All right. How about A? 32.930. It's uncertain in the third decimal. So that's not it. Right? Certain digits, uncertain digit. How about B? 3.02 times 10 to the 6th. Times 10 to the 6th. Uncertainty of 0.01. Right? That's not 0.01. Because what would that be? That would be 1 times 10 to the minus 2. And that's a positive. Right? So that's not right. Did I lose anybody? I get those blank stares again. How about C? 3.0 times 10 to the minus 1. All right. So what would this be in standard notation? We'd have to move the decimal what? To the left. And both of those are significant. So it'd be 0.30, right? And that last one, significant digit, is uncertain. So C is the correct answer. Right. Moving into the centuries. 102. Density can be used as a conversion factor to convert from. Well, let's look at the definition of density. Equals mass per unit volume. Right? Okay. If we use only density, then we have a mass unit. Let's just make something up, say grams and milliliters. So this could convert from volume to grams. Right? If we have a volume over here of X milliliters, and we use the density equivalent, would be some mass in grams divided by volume in milliliters, then the milliliters would cancel and leave us with grams. Right? So we can convert from volume to mass. So B looks like it's a good candidate. Volume to mass. Based upon that logic, we skipped over A. Let's see. Mass to volume. What would you do if you had mass and you wanted to convert to volume? X grams, and you wanted to convert to volume. Grams on the bottom, milliliters on the top. So that'd be volume mass. That would work too, wouldn't it? Because remember, all you have to do here is flip those. All conversion factors are equal to 1. So if it's this way, equal to 1, that way is also equal to 1. Right? What do you get when you flip 1? 1. Okay. So B and A would also be true. How about C? Metric unit mass to English unit mass? No. This density, you don't convert mass to mass with density. You have to have mass and volume involved, right? So C can't be it, and that means 2 of the above are correct. More than one are correct. That's D. So D is the correct answer for this one. This equivalent to density is a valid conversion factor for going from volume to mass or mass to volume. (103). The density of table sugar is 1.59 grams per milliliter. I would have expected grams per cubic centimeter, but the same difference. It is true that 2 grams of table sugar occupies a volume of 1.17 milliliters. All right, so we got to figure out what's the volume equivalent for this sugar if we have 2 grams, 3 grams, and 5 grams. So here's where I like to use Henry Ford, right? Assembly line. So our A, B, and C possibilities. 2 grams, so 3 and 5. 3 grams and 5 grams. We want to convert these using that density as our conversion factor. Right? Here's my assembly line. So we need grams on the bottom to cancel the grams and leave us with milliliters. And we've got the same substance, so it's going to have the same density each. So 1.59 in the denominator. There we go. All right. So the first one says that the volume is going to be 1.17. Well, we can use the calculator, right? If your mind gets foggy during a test, it's probably good to do this rather than try to estimate it with pure brain power. Right, that's 1 point, let's see, 3 significant figures. 1.26 milliliters. Okay. Well, that was not it. How about 3 divided by 1.59? 1.89. Okay. That's not it. How about 5? 5 divided by 1.59 is 3.14. That's it. Right there. C. Okay. Everybody knows that that's what Henry Ford was famous for, right? The assembly line. Okay. Get your workers lined up, and each worker does the same job over and over and over again. Kind of boring, but it produces cars really fast and cheap. And he said you can have any color you want, as long as it's black. That was for the Model T. And for the moment, we'll discount the fact that Henry Ford was a racist. Okay, chapter 3. All right. Chapter 3, 120. The nuclear charge for an atom of fluorine is what? Okay, so we have fluorine, 9 and 18, right? This is the Z number, the atomic number, and this is the mass number, A, abbreviated A. And it represents protons plus neutrons. What's the nuclear charge? Think of the atom as very dense nucleus with electrons out here. Right? So how many protons does it have here? 9 protons, right? And 9 neutrons, which have no charge. And then you got 9 electrons out here. That makes the atom neutral. But what's the charge on the nucleus? Plus 9, right? Plus 9 is the charge on the nucleus. That's what that means, nuclear charge. Now, if it says, what's the atomic charge? That would be 0. Because taking the whole atom together, you get 9 pluses and 9 negatives that cancel each other out. But to answer this question, the nuclear charge is plus 9. I already gave you the answer to the next one. 121, yeah. The quantity A gives the number of what? A and Z. So what does A mean? It's the number of protons plus the number of neutrons. Or, we may not have covered this in class. Protons and neutrons are called nucleons because they're in the nucleus. Right? So the nucleons in an atomic nucleus represent A. Protons plus neutrons. Okay? I think that's why I put that one in here, because we don't cover it in the lecture. We call them protons and neutrons, and we don't classify them together as some books do. And your book probably does call them nucleons. Has anybody read the chapter? Sped read it. Can you write reading, or do you read write? Starting to sound like Jethro Bodine. He was going to be a famous international playboy one time. The other time he was going to be a brain surgeon, and then he was going to be a double knot spy. Nobody remembers the Beverly Hillbillies. Okay. Max Baer. I don't even know if he's still alive. I know Ellie Mae's gone. I can't remember her name, though. She was Miss Louisiana before she got into television. 2 naturally occurring isotopes exist for the hypothetical element Dipium. 25% of dipium atoms have a relative mass of, let's see, what are we going to use for the symbol? Di? There's no Di up there, so we can use Di. So 25% have a relative mass of 17 atomic mass units. 17 atomic mass units, 25% have that. Okay. Another isotope has 75% is 21.3 atomic mass units, 75%. So we're saying that this dipium only has two isotopes, that one and that one. What's the atomic mass of dipium? Right. What would we put in the periodic table in the upper left-hand corner of each one of its square? How do we calculate it? Remember? It's weighted average. So this represents 25% or 0.25 of the whole. So what's 0.25 of that value? It's 4.25. Okay. And 75% of 21.3 is 15.975. I'm going to keep those. Then we add those together. 5, 2, 1 11 is 12, 1 9 is 10, 20. 20.25, and we have to round it off this one. So 20.23 is what I would say is the average atomic mass. Best answer, C, 20.2. Okay. That's how you calculate the average atomic mass for an element if you know the abundance and the individual masses of its isotopes. #125. The modern periodic table arranges the elements in order of. That's just memory. Now, originally, Mendeleev arranged the elements in order of increasing mass. Right? But when Henry Moseley put his thumb on the atomic number, and we made the association between, he didn't do it later, they made the association between his atomic number and the number of protons. Then the table was now ordered by the number of protons, which is D. Okay. Upper left, lower right, right? You're increasing number of protons, one at a time. And we've discovered every element, or created every element up through 118. That's as far as we've gone. Unless you're the Wolverine, and then there's that other element. What they inject into his bones?
Adamantium.
Adamantium, yeah. Right. I still haven't found it on the table. 126. Yeah, 126. In which of the following pairs of elements are both members of the pair in the same period in the periodic table? So when you're looking at the periodic table, what's the period? It's the rows, right? So these elements need to be in the same row. How about neon and magnesium? Let's see, let's find neon. There it is over there on the right. Second period, below helium. Cross, magnesium is not in that one. Right? How about B? Nickel and palladium. Right? So those are both transition metals. Nickel, you can see right there, is number 28. Palladium is right below it. It's in the same group, but it's not the same period. Right? So that was out. How about C? Calcium and selenium. Let's see, calcium over here on the left, see it, Ca. Follow it across. Yep, there's selenium, 34. That's the one. Right, we can stop there. Potassium and rubidium are in the same group, not the same period. Oh, electronic configuration. You guys mastered that already? Have you been practicing it? Correct electronic configuration for, let's see, 128. I'm going to write it down here. For chlorine, they even give you the atomic number. Right? So what's the order? 1s, 2s, 2p, 3s, 3p. It's probably enough. So let's start filling it in. How many electrons in the s orbital? 2. 2. How many can we put in the p orbital? We can put a maximum of 6, but you're right. Well, no, wait a minute. We've used up 4. 13. Okay, so we need to fill that one up. And that's minus 6 is, we got 7 more. So 2 from that to 5. So this one has 5 in it. Okay. So that would be C. C would be the best answer there. Now that's knowing the order and just filling them in, right? Using the alphabet principle. Lowest energy first, and you keep adding them up. But if you know how the periodic table is arranged, and we're looking at chlorine over there on the right, 17 chlorine and the halogens, then we know that the first period finishes off the 1s orbital. That first period is 1, and it only has s in it. The second period, right, lithium, beryllium, that finishes off the second s. And then we get to the p's, right? The right-hand side is p's, like boron, carbon, nitrogen, oxygen, fluorine, and neon. Then we swing back around and catch sodium. Now we're in the third period, catching S for sodium and magnesium. And then we skip over to aluminum, that's 3 P's. Right? And aluminum goes 1, silicon 2, phosphorus 3, sulfur 4, chlorine 5. And then you can put what belongs in each one of these. Okay, you can do it that way too. Then you don't have to remember this order, or you don't have to use that diagonal diagram. That was 128. All right, 131. How many unpaired electrons are present in the orbital diagram for an atom whose electronic configuration is 1s2, 2s2, 2p4? Okay, 1s2, 2s2, 2p4. We're looking for unpaired electrons. Okay, now we're talking about Hund's rule. All right, how many suborbitals are there in P? There are 3 of them. Think of it this way. If you know that P can hold a maximum of 6 electrons with only 2 in each orbital, then you can only have 3, right? 2, 4, 6 maximum. But we're going to put 4 electrons in there, according to Hund's rule. So you put 1 in here like that, like that, like that. That's 3 of them. Now you can start pairing them up. Right? So we have 2 unpaired electrons. Okay. Circular nods. My favorite. By the way, which one was that? 4 plus 4 is 8. That would be oxygen, right? That's oxygen. All right, 135. Which of the following statements correctly describes the subatomic particles called a neutron? Right? A neutron is like that, right? Has no charge, and it's about the same mass as a proton, just a hair bigger. Has a mass slightly less than that of a proton? No. Is not found in the nucleus? No. It's definitely a nucleon. Has a positive charge? No. It's a neutral. So none of those are correct. All right. Let's see who's next. 136. Which of the following statements concerning the nucleus of an atom is correct? All right. It accounts for almost all the mass of an atom. Is that correct? Yep, sure is. B, it is always positively charged. Yep. Nucleus, yes, always positively charged because there are only protons there along with neutrons. Positive charge. It contains only neutrons. See? Nope. Protons and neutrons. Except for what? Hydrogen. The isotope of hydrogen. One proton and only one proton, no neutrons in that isotope. But everybody else has neutrons in there. Okay, so let's see, 136. That means more than one correct answer. Right? A and B are correct. $137. Which of the following collections of subatomic particles possesses a net charge of +2? Collection of subatomic particles. Okay, a net charge of +2. That's what we're looking for. All right. How about A? 2 neutrons and 2 electrons. There's no positive charges in that one. How about B? 3 protons and 1 electron. Yeah. 3 positives and 1 negative, right? That's good. See, we got some wonky ones, so we better look at C also to be sure. C, 3 electrons and 1 proton. No, that's a -2. So that's not it. So B is the right answer. There's only one right answer in that one. And we get these two in. $142. Nobody thought of one that was giving you trouble? Okay, but just keep going then. Period number and group number in the periodic table are numerically equal for which of the following elements? All right, so you have to be able to count period number and group number. And when we say group number, I think that they're interested in the new version, 1 through 18 from left to right. I think. Just taking a quick look at those, they might be basing it on the Roman numeral. Right. So let's see what we got here. Aluminum is group period. Group period. Okay, so aluminum has Group. That's 1, 2. Yeah, they're talking about Roman numerals. So 3A for aluminum and 3 period. Right. So group is Roman numeral 3 and period is third row. How about B? Arsenic. Let's see. Arsenic is over there on 1, 2, 3, 4, 4 down and 5 to the right. So it's 5 here and 4 period. How about C? Antimony. SB. Okay, that's 5 and 6. 6 period. And 5 here. So that's wrong. All right. More than one correct response. More than one correct response. SB. 5 and 6. Oh no, I was reading that wrong. That's 5. That's right. 5th period. Yeah, so we got 2. We got this one and that one are both correct. If you use the Roman numeral system. Okay. That's the catch for that one. Maybe that's why I put it in there. So we'd be sure and cover it in class. All right, 143. Which of the following periodic table groups contains 3 or more non-metallic elements? All right, non-metallics. So if we're over to 3, how many non-metallics are in 3A? Just 1, boron. It's the only one to the right of that line. Okay. 4A. All right, 4A would be 2, carbon and silicon. How about C? 5A. 5A. That's the pnictogens. Nitrogen, phosphorus, arsenic. So that's 3. 3 or more non-metallics. All right, so that's it. C. Okay. You have to know where that line is. The divider between metals and non-metals. Let's see. Yeah, we can get both of those in there. 145. Which of the following electron configurations corresponds to an element in the same group of the periodic table as the element whose electronic configuration is 1s2, 2s2, 2p5. 1s2, 2s2, 2p5. Okay. We're looking for the electronic configuration that's in the same group as this one. And what's characteristic about the groups is they have the same valence electrons, number of valence electrons. So this one has 7 in an S and a P. 2 in the S, 5 in the P. So which ones are those? A is 2 and 4. B is 2 and 6. That can't be it. C is 4s2. None of them are right. Right? There's no correct answer there. Everybody see that? $146. All right. Two unpaired electrons are present in the orbital diagram of which of the following elements? All right, two unpaired electrons. So if we have carbon, neon, and magnesium. Okay. What is present in the orbital diagram? Okay. So where are the unpaired electrons going to be? If we have any, they're going to be in the highest orbitals, aren't they? Right. Okay, so what's the highest orbital of carbon? Carbon has 2p2. Both of those are unpaired, right? Because they're like that. Neon's got a complete. Right? It's 2p6. So they're all paired. Magnesium has a 3s2. Right? Because got those paired. Right? So carbon is the only one that has two unpaired. Okay. Now, why do we even care whether they're paired or not? I missed one there. Well, I don't think we're going to cover it in this class, but there is one characteristic physical measurement of an element. It's called, if my mind doesn't freeze up, diamagnetism versus paramagnetism. Those are measurable quantities. And we can trace them to whether or not the atom or the element has paired electrons in it. Right, that's enough said on that topic. Since you're not going to be responsible for it, I don't need to beat you over the head with it. 162. Choose the correct atom that has a nuclear charge of plus 17. Plus 17. Nuclear charge. So that means 17 protons, right? Well, that one should be easy. Chlorine. Chlorine has 17 protons in its nucleus. That's it. And keep it going, keep it going. Here we go. 169. We ought to be getting close. Choose the appropriate pair of atoms that contain the same number of subatomic particles. Okay. Subatomic particles. That would be protons, neutrons, and electrons, right? Okay. So let's work these out. Carbon, 6 and 13, has how many subatomic particles? Well, the protons and the neutrons are added for us right here. 13. How many electrons? If this is neutral, it's got to have 6 electrons, right? So it's 19 subatomic particles. Right? 6 plus 3 is 19. How about B? Oh, nitrogen, excuse me. Nitrogen, 7 and 13. Right? 13 plus 7 is 20. Right? So that's not it. Chlorine, 17 and 37. Right? So 37 plus 17 is 54, right? Subatomic particles. And argon, which is 18 and 36. So 36 plus 18 is 54. So that one's a good one. Do we have any? There are no wonky ones in there, so we found our answer. B. The key there is to watch out for the terminology. Subatomic particles. That includes everything. $175. Choose an appropriate pair of elements that are in the same period of the periodic table. We did one like this already, didn't we? The same period. Yeah, they're in the same rows. Rubidium and strontium. Yeah. Right there in period 5, right next door to each other. Right, so that one works. Oh, we found our answer. We don't have to go any further. All right, gotta be getting close. Yep. Okay, what else do I have down here? Just the periodic table? Yeah. Okay. All right. Let's see. Coming up on 11. Is it 11 o'clock when our 10:55 is when the lab starts? All right, so I got 5 minutes. Maybe I forgot to hand out the lab last week. Is that possible? Or did some of you leave and I handed it out after you'd already gone? Right. If this happens again and you see in the schedule there's a lab coming up, print yourself a copy or at least call it up in Brightspace and read it. Right? Because what's the number one safety factor in laboratory work? Know what you're going to do before you walk in. Right? If you're going to walk in, and who in here cooks? Right? From a recipe sometimes? Right? Right. If you're going to cook something, do you just walk in the kitchen with your recipe and start pulling things together? You may not have everything you need, for one, and you may not know where everything is. Right? You read the recipe and you say, what do I need to do? Right? Is it a recipe that you have to prepare this one first and it takes a long time, and then this one takes a little time, and you wait and prepare it later and put them together? Like I don't know, meringue on a pie. Right? The meringue comes later. Once you get the pie mixed up, then you make the meringue and slap it on top, shove it in the oven gently, and maybe get the little peaks to brown up a little bit. Okay, so I'm going to stop this share. If there are no questions, then we're done with the review, and next week we'll have the exam first thing. And let me be sure my schedule's right. Yeah. Exam, and we'll cover chapter 4 afterwards, and no lab. So just checking. Right. I don't have a lab on days when we have exams. So this lab that we do today, since we don't have a lab next week, it won't be due until the week after that. Right. That's my pattern. Previous labs are due on the day we walk in for the very next lab in the sequence. And that could be the next week. It could be 2 weeks if there's a intervening exam. This is exercise 3. We did safety, then we did graphing. Yeah, lab techniques. This is 3. Lab number 3. Prelabs. Questions. All right, 1A. In the design of the Bunsen burner, what's the purpose of the gas control valve? It's not a trick question. Yeah, right. It controls the flow of the gas. Right. How about B? How about the air vents? Right, that little collar around the bottom. Now, some of them have a screw thing. Right, I see one there. So in order to change the air for that one, you screw it clockwise to go down and tighten it up and choke it off, or you counterclockwise to bring it up and let more air in. Right, but the air control valve does what? Yeah, it controls the amount of air into the mixture. Right, so we got those 2. How about 2? Why is a luminous yellow flame often smoky? Okay. Natural gas. methane plus oxygen yields carbon dioxide plus water. Right, let's see. That's not balanced. Okay, it's not balanced, so forgive me for that. But this is complete combustion. If you have exactly the right amount of oxygen for the methane, you get carbon dioxide and water. If you choke it off, if you limit this one, then what you're going to do is with all the extra heat, you're going to cause this one to decompose and not combust with oxygen. So when you get decomposition of hydrocarbons like this, they usually produce carbon solid, soot. Okay? And anybody that's got a fireplace, you know about soot. Periodically, you have to have your chimney swept out. Otherwise, you could have a chimney fire. Okay. So when that soot, and when you choke off the oxygen and you start creating that soot, what does it do? Well, it's still there, and it's being heated, right? And it luminesces, right? You heat it hot enough, and it turns yellow, right? It gives off light. Doesn't give off much light, but it gives off some. And that's where the yellow flickers that you see in there, that's where they come from. So why is luminous yellow flame often smoky? Incomplete combustion makes soot. Okay, 3. A student wanted 20.000 grams of salt. 20.000 grams of salt. They want that. Right? Which balance should the student use in order to obtain the most accurate quantity? A platform triple beam, a single pan. The triple beam platform they're talking about is actually our hanging right here, the big one. The single pan is the little one, right? Least accurate, next accurate, top loading balance, most accurate. Right, 3 decimal places. That's the top loading balance. And it's because, explain why you would want to choose that one. Because it's accurate to 3 decimal places, right? Thousandths of a gram. 4. Explain the difference between precision and accuracy. We did that in class, didn't we? Right. What's precision? I'm sorry?
Precision, it's like, I remember it like an aircraft. It's like you'll have the same like measurement. It'll be like most measurements, they're like nearly the same.
Precision. It's a measure of how close multiple measurements are to one another.
Yeah, like arrows. Precision.
Right. And accuracy. I'm sorry?
It's like like the exact measurement.
Right. You have an accepted or a true value. How close is your measurement to that true value? Now, that can be a single measurement or it can be an average of several. Right. So if we have a bullseye and we have a measurement here and here and here and here, that's accurate because the average is right there. But it's not very precise because they're really spread out. Okay. 5. Is this the last one? Yeah. 5 is the last pre-lab question. All right, A. We've got to solve the problems, record the answers to the proper number of significant figures. All right, so we've got a difference between, actually we've got add, subtract rule, we've got multiply, divide rule, and then we've got a combination. All right, the first one is the subtract rule. All right, so this would be 21.65 minus 3.2. All right, we line up the decimals. So what would that be? You got a 5, yeah, we got a 5 there, we got a 4 there, 3 from 11 is 8. That's a 1, correct? Let me see if I did that right. 6. Yeah. But where's the uncertain digit that limits? This one right here. It limits us to this one. So it'd be 18.5. Okay. How about B? What type of rule is that one? Oh, that's a mix. So what's the order of operation? Parentheses first. So we got 4.583 plus 2.108. 4.583 plus 2.108. That's 11, 9, 6, 6. And we can keep all of them, can't we? Right, because they have the same uncertain position right here. And then that one is divided into 4.4.01 divided by 6.691. Right, so I need my calculator for that one. Let's see, 4.01, 6.691. Okay, I get 0.59931. 99931. How many can I keep? 3 significant figures. This is a multiply divide rule. So I just go for the least one, and my answer can have 3 significant figures in it. What did I say? Is that 1? That's a 1. Right? 1, 2, 3. This is less than 5, so that drops out, and I keep that 0.599. 3 significant figures allowed, based upon this part of the operation. That's a compound operation that has to follow the rules, the orders of operation. So, how about C? 6.15 divided by 1.2. Uh, 5.125. Right? So we're limited with this operation to 2 significant figures. So chop it off there. That's less than 5. So we can only keep those 2.